Hello, my name is Han Tran, and in this video we're going to be focusing on adiabatic flame temperature. So to take a closer look at adiabatic flame temperature, we're going to be looking at a burner. We are told that this burner has natural gas and air going in. We are told that the natural gas is comprised of 95 mole percent methane, 4% ethane, and 1 mole percent propane. And as for the air, we are told that there is a 20% excess, and we know that air is composed of 21% oxygen and 79% nitrogen. So when we're taking a look at what the temperature of the flame would be, we know that the enthalpy of what's going into the burner has to be the enthalpy of what's coming out of the burner, aka the flame. So at a steady state, we can conclude that the enthalpy per unit mass going in multiplied by the change in mass minus the enthalpy coming out per unit mass multiplied by the change in mass in for enthalpy going in and change in mass out for enthalpy going out is going to be equal to 0. So the total enthalpy in is equal to the total enthalpy out. This fact is very important as we continue to look at how to solve for the temperature of the flame. In addition to the enthalpy, what we have to know about this in order to calculate the temperature is the reaction that's occurring in the burner. So what's happening is the natural gas is combining with the air to create a combustion reaction. So we're going to write out the equations for these reactions and balance them accordingly by adding moles of each to make sure that the equations are balanced. So we're going to start with the first component of the natural gas. And so we're going to start with the methane. And the methane is combining with the air. So the air is comprised of oxygen and nitrogen. And as the methane combines with the air, it's producing carbon dioxide and water as its products. And so in a normal combustion reaction, it would just be the methane reacting with oxygen to provide carbon dioxide and water. And as we can see in a combustion reaction, there is no nitrogen that's being reacted, but since we are combining with air, there's nitrogen present in the air. And so since the nitrogen is not getting reacted, it goes into the reaction and it comes out the reaction the exact same. And so we have the nitrogen on the right as well. So now we can begin making sure that the moles of oxygen, the moles of nitrogen, the moles of carbon and hydrogen are on balance on both sides. But before we go on to do that, we have to note that there is 21% oxygen and 79% nitrogen in air. And so they're not in equal parts. So we have to account for that by making sure that we add more of the nitrogen. So since it's a 79 to 21 ratio, if we add 79 over 21, that will make sure that it is accounting for how much air or how much of the nitrogen is in the air in respect to the oxygen. And again, whatever goes in to the reaction, since the nitrogen is not getting reacted, also comes out. So we must also add the 79/21 to the right side. So now that our air is accounted for, let's start counting the carbons, oxygens, and hydrogen. So we'll start with the carbon. On the left side here, we have 1. So for carbons, on the left side we have 1, and on the right side we also have 1, so those are balanced. On the left side for hydrogen, we have 4, and on the right side we have 2. So we need to add 2 more hydrogens to balance it out. So in order to do that, we're going to make it 2 moles of hydrogen, 2 moles of water, which will increase the hydrogen number to 4. So now that is balanced. Now let's take a look at the oxygens. On the left side we have 2, and on the right side we have 2 for the carbon dioxide and 2 from the water to give us 4 oxygens. And so we need to increase the number of moles on the left side of oxygen so that it is balanced. So since there is 2 less, we'll add 1 more mole of oxygen, which will give us 2 moles of oxygen to give us 4. So now the carbons, hydrogens, oxygens are now all balanced. But we have to keep in mind that as we increase the oxygen, the moles of oxygen, we also have to increase the moles of nitrogen because they are in air together, and so they work coinciding together. And so since now there's 2 moles of oxygen, we have to have 2 moles of the nitrogen. And again, nitrogen does not react, so whatever goes in comes out. And so there will be 2 on the right side as well. And so that is our equation for the methane. And so we're going to move on to the second component, which is ethane. So we have the ethane reacting with the air. So we have oxygen and then 79 parts nitrogen for 21 part oxygen of nitrogen. And that's going to again have carbon dioxide and water as the products, as well as nitrogen. So we're going to follow the same process that we did for the methane. So we're going to count our carbons. On the right side we have 2, and on the left side we have 1, so we have to increase the number of carbons. So if we increase the moles of carbon dioxide from 1 to 2, that will give us 2 carbons, making that balanced. Now let's take a look at our oxygens, or our hydrogens, excuse me. On the left side we have 6, and on the right side we have 2, so we have to increase it to get the same number of hydrogens. So if we increase the number of moles of water from 1 to 3, the 3 multiplied by the 2 will give us the 6. So that is now balanced. So now let's take a look at our oxygens. So we have 2 oxygens on the left and 4 oxygens as a part of the carbon dioxide, plus the 3 oxygens as a part of the water, which would give us 7 oxygens. So since we have 7 on the right and 2 on the left, we have more on the right, so we need to increase the number of moles on the left. So if we have 7 halves, that will give us 7 oxygens on the left, which will make the oxygens balanced out. Again, whatever we do to the oxygens, we also have to add on to the nitrogen since they are together in the air. So that'll be 7 halves on that nitrogen on the left, and whatever goes in nitrogen-wise will also come out. So we have to balance that out on the right as well. So moving on to our last component of the natural gas is we have propane. Again, the propane will react with the oxygen and the nitrogen in the air to give us carbon dioxide and water, as well as the nitrogen that was originally in the air that did not react. So now let's take a look at balancing out like we did with the previous two equations. So for carbons, we have 3 on the left and 1 on the right. So we have to add moles to the carbon dioxide to increase the number of carbons. So if there are 3 moles, that would give us 3 carbons. That is now balanced. Now we take a look at our hydrogens. So on the left, we have 8, and on the right, we have 2. And so we have to increase that to 8 in order for them to balance. So if we have 4 moles, that's the 4 multiplied by the 2 will give us 8. So that gives us the 8 that we desire. Now we take a look at our oxygens. So on the right, we have 2, and on the left, we have 3 from the carbon, or excuse me, 6 from the carbon dioxide and 4 from the hydrogen, which gives us 10. So if we have 5 moles, that will give us the 10 oxygen, 5 multiplied by 2. And so now that is our balance. Again, whatever we do to the oxygen, we have to also do to the nitrogen since they are together in the air. So we have to put 5 moles of the 79 over 21 moles of nitrogen, and then whatever nitrogen goes in will also come out since it doesn't react. So we have to do the same on the right side. And so those are our 3 balanced combustion reactions. So now that we have our reaction equations, we're going to go back to what we were talking about earlier about how the enthalpy that's going into the burner has to equal the enthalpy coming out of the burner. So the reaction between the natural gas and the air going into the burner, that enthalpy is going to equal the enthalpy of the flame. So we're going to talk a little bit about heat capacity and change in enthalpy. So heat capacity is defined as the change in enthalpy with respect to temperature at a constant pressure. And so when we're talking about the change in enthalpy, that's going to be the heat capacity, so the change in enthalpy with respect to temperature at a constant pressure. And that's going to be with respect to a change in temperature. And so since the pressure is constant and this is an ideal gas, we're going to not write out the effects of pressure. And so this is the equation for the change in enthalpy. So if we were to take the integral of this, we would have the change in enthalpy is equal to the heat capacity multiplied by the change in temperature. Now, on this first equation up here, the change in temperature is small, so that it can be assumed that the heat capacity is constant. But in the second equation, the range in the temperature change is unknown, so it cannot be assumed that the heat capacity is going to be constant. So what we have to do is we have to take the integral of the change in enthalpy from temperature 1 to temperature 2, and so that's going to give us the integral of the heat capacity dependent on a change in temperature from temperature 1 to temperature 2. And so we're going to take a break from this writing out the equations and actually head on over to take a look at our code. And so right now we don't have anything, but what we're going to be using for this code is a repository, which is just a bunch of pre-written codes that give us a bunch of data and tools. So as we can see, if we were to look at the data here, there's all these different properties for all these different compounds, and so we're going to be using this in our code to gain the properties that we're looking for. So we're going to import this repository into our code, and so we're going to copy the link for this repository, and we're going to use !git git clone, and we're going to paste our repository in, and we're going to shift enter, and this will clone all the data from this repository into our code. So now that we have that repository imported, if we go over here in our contents and we look, we can see that we have CHE tools completely loaded in. with the data of all the different components and compounds and their properties, as well as the different tools that we are now able to use. And so now what we have to do is we have to add in our code a way for it to read this new repository. So we're going to import something called sys, S-Y-S. What sys does is basically helps us locate what we're going to be using within our own code in the repository. Somewhat like an interpreter, it's going to take what we need and go look for it. So we have to tell it where to look. So we're going to use sys.path.insert. And so this is us kind of telling us where to look, telling the code where to look. So we want it to first look in content. So that's the content that our table of contents. And then what it's going to go to next is the CHE tools. And that's this folder here. So that's where it will find everything. And then since we're importing things, we're going to import them all at once. So we have it all at the top. So we're going to import numpy as np. This will allow us to do many mathematical operations. Also from scipy.optimize, we are going to import the root. So this will help us solve for a root of an equation. And lastly, we have to import the CHE tools. CHE, so that's import tools.che as CHE. So what that does is it allows us to use the tools that we've just imported. So let's use the repository that we just imported to obtain the properties of the different components in our problem. So we are going to name it P for properties, and we're going to use the CHE, and we're going to look at the props, so PROPS, and we're going to have to give it all the different properties of whatever we need. And so the first one that we need is the methane. So if we go over here, we can see that methane is right here. So we need methane. We also need ethane, which is right here. We need propane, which is down here, so it's N-propane. We will also be needing oxygen. So that's right here. Nitrogen. Carbon dioxide. Water. So what we did was from our reaction equations up here, we just put in all the different components that we will be needing, and that we are going to retrieve them as an array. So it's going to give us to them in a list. We're going to shift enter. So those are all of our components and their properties. So if we take a look, let's just take a look at, methane's properties, and we'll take a closer dive into what all is in here. And so these are all the physical properties, or majority of them, for methane, and this is taken from ChemCAD. A lot of these equations down here are. And so like we are given its molecular weight, critical temperature, many properties. And so what we are interested in for our equation over here is the heat capacity of an ideal gas. And so if we look at the property here, and we scroll down, let's see if I can find it. Here it is. The ideal gas heat capacity. in joules per kilomoles Kelvin. And this gives us the adiabatic capacity of methane, but it also tells us the equation in which we can find it in ChemCAD. So if we go over here to ChemCAD, this is the physical properties user's guide for ChemCAD equations. And if we were to scroll through and look for equation 107, this is the equation that is used to find the heat capacity of an ideal gas. And so we are going to copy this equation into our notebook over here that has all of the equations that we are deriving and working on. This equation says that the heat capacity, in this case it's referred to as Y on the left, is A plus B multiplied by C divided by temperature divided by the hyperbolic sine of C divided by temperature, that whole quantity squared, and then plus D multiplied by the quantity of E divided by temperature divided by the quantity of the hyperbolic cosine of E divided by temperature, that whole quantity squared. And so now that we have this equation for the ideal gas heat capacity, we need to find the integral of it with respect to temperature. So we're just going to take this information here. And since A, B, and D are constants, we're just going to be finding the integral of these parts. So we're going to be heading on over to Wolfram alpha. And putting this first part into the integral calculator. So we're going to do integral of, it's going to be C divided by temperature divided by the hyperbolic sine of C divided by temperature, and it's going to be that whole quantity squared. And we are finding this with respect to temperature. So we're going to enter, and that will give us this equation here. And so we're going to copy that on over. That's going to be C hyperbolic cotangent of C divided by temperature. So now we're going to move on and do the second part over here. And so the equation is relatively the same, other than it is E instead of C, and it is hyperbolic cosine instead of sine. We're going to keep everything else constant, and we're going to shift enter. And so that's going to give us negative E hyperbolic tangent of E over T. So we're going to copy that on over as well. So we have this is equal to negative E hyperbolic tangent of E over temperature. So those are the integrals that we can find using the equation. That's going to be from temperature 1 to temperature 2. So if we were to rewrite this equation, it would give us A plus B C hyperbolic cotangent of C over temperature plus D minus, so we're going to change this plus to a minus, E hyperbolic tangent of E over T. So what we're going to do with this integral that we just found is simplify it a little bit, so when we put it into our code, it will work a little easier. So we'll have A plus B times C times, so the hyperbolic cotangent is equal to the 1 over hyperbolic tangent. So it'll be 1 over hyperbolic tangent of C divided by temperature minus D times E times the hyperbolic tangent of E over temperature. So now we can go about copying that into our code. And so what we need to do in our code is define a function so that it will return to us the value of this integral. And so we're going to define a function, we'll call it integral of heat capacity, so Cp, and the value that we are going to give it is the temperature. And so we want it to return this equation. So this equation, we'll put it to the side here so we can look at it as we copy it. So it's going to be A plus B multiplied by C divided by the hyperbolic, so we'll use numpy, hyperbolic tangent of C divided by temperature. And minus D multiplied by E multiplied by the hyperbolic tangent of E divided by T. So what are these variables, the A, B, C, D, and E? Well, if we take a look back at our properties and we look at this ideal heat capacity equation, we can see that there are coefficients, and there are 1, 2, 3, 4, 5, A, B, C, D, E coefficients. And so those are the coefficients for the A, B, C, D, and E. And so what we have to do is we have to get those coefficients. So to get that, we're going to use the P. This is the properties that we defined earlier. And this is the ideal heat capacity. So if we were to look at, let's just say IG, CP, IG, that's the ideal heat capacity. That's what it would be. And so if we were to get the first coefficient here, we can see that it matches the 3,000 or 33,295 that's here for the methane. Again, it's for all of the properties. So the first one we're looking at here is the methane. We can see that it lines up. So we need to use these values. So we need to use A, B, C, these coefficients in this equation. So we're going to replace the A with the P dot CPIGA. B will be P dot CPIGB. And so all these variables will be replaced with the coefficient that is from the ChemCAD equation in the properties. So now if we shift enter, we have everything defined and we have the integral that will return. So if we were to do the integral at, let's say, 1,000 degrees Kelvin, that would return to us the heat capacity of that ideal gas at that temperature. Now what we can do now that we have the heat capacity of an ideal gas at any given temperature, we have that equation. We can do this to find the enthalpy for any given temperature, because there is, in all of these properties, there is a heat of formation of an ideal gas. And so the heat of formation is how the compound is formed, the amount of energy and heat required for that. And so we have, again, another property of these equations. And so we have the heat of formation. So if we were to shift enter, again, we're looking at methane. We have the negative 74,850. And so that is our heat of formation. And so when we change the temperature, what's happening is the heat is actually going to increase by the difference between the heat capacity at whatever temperature we're being changed to and the temperature at 298 kelvins, which is the normal temperature. And so we'll do plus the difference between the integral of whatever temperature, right now we'll say 1000, minus the integral Cp at 298. And so these are the temperatures at the specified temperature here. And so we can actually define yet another function. We can call this function h, because what it's going to do is it's going to find the enthalpy at that given temperature. And we want it to return this equation here. And so now what we can do is, if we were to shift enter, we can find the enthalpy, let's say at 1000. Those are the enthalpies that we did earlier. It's just now in a function for us to easily access. So now what we must do is we have to go in and look at the different moles. So this is why we looked at the reaction equations that we did at the beginning of the video. And so we're actually going to use the tools that we have developed. So the two functions that we've defined, the function for the heat capacity and the function for the enthalpy, we're going to use those tools to actually solve this problem for the temperature of the flame. And so to begin that is we're going to input the number of moles that are in this problem. And so we have the fuel, which is the natural gas, and there is an array of those. So we're going to put it in the same order that we have the properties at. So we have methane, ethane, and propane. And so we have 0.95 because we have 95 mole percent methane. Then we have 4%, so 0.04, 4 mole percent ethane, and then we have 1 mole percent propane, so 0.01, and that is our fuel. And so now what we have to do is input the number of carbons and hydrogens per mole of each of the components of the fuel. So we will name this fuel CH. And so for the first component, there is 1 carbon and 4 hydrogens in methane. And for ethane, there are 2 carbons and 6 hydrogens. And in propane, there are 3 carbons and 8 hydrogens. And so now we have two arrays, one that has the moles of each component in the fuel, and then one that has the number of carbons and hydrogens per mole. And so if we multiply the two arrays together, we can get the number of carbons and hydrogens total. And so if we multiply arrays, we're going to do fuel, @ symbol is to multiply arrays, and we're going to shift enter. That gives us the array, and so the first number is the carbon and the second number is the number of hydrogens. So if we break down the array, so we have number of carbons, number of hydrogens equals that. We're going to shift enter. That means we can use this to find the number of carbons. So if we were to change the number of moles in the starting fuel, it would change it all for us. So now what we have to do is use the number of carbons and hydrogens to figure out the number of oxygens and nitrogens and carbon dioxide and water that is produced. And so we can use our reaction equations that we established earlier to help us do so. So we can see that the number of carbon dioxides are equal to the number of carbons. So the number of carbon dioxide is equal, or the moles of carbon dioxide is equal to the number of carbons. Now if we take a look at the oxygens, or let's first look at the hydrogens. If we look at the hydrogens, we can see that the number, or excuse me, look at the water, not the hydrogens, but we're going to use the hydrogens to figure out the number of water moles. So we can see that the number of water moles is equal to the number of hydrogens divided by 2. So here for the methane equation, we have 4 hydrogens on the left and 2 moles of water on the right. For the ethane, we have 6 hydrogens on the left and 3 moles of water on the right. So it's just the number of hydrogens divided by 2 to get to the moles of water. So now if we take a look at the number of oxygens, that is equal to the moles of water molecules divided by 2 plus the moles of carbon dioxide. And if we take a look at the nitrogen molecules, it is the moles of the oxygen multiplied by 79/21. And so those are the number of moles for each. Another thing that we must consider when we're inputting all this information is the fact that we have an excess amount of air. So we were told in the problem that we have 20% excess air, and so we have to take that into consideration. So we have 20%. Well, what does that 20% mean? Well, that means when we're looking at the number of moles of oxygen, we have to realize that that has to be multiplied by the amount of excess air. So that's going to be multiplied by 1, which is the value that there is, plus the excess air percentage. So now that we have all of this inputted, we can start looking at the moles going in and the moles coming out. But before we do that, we're going to go back to this enthalpy here, because we're going to be using that later on to compare if the enthalpies are the same. But if we were to take the enthalpy of 1,000, would that be accurate? Well, the reason that it's not accurate right now is because if we look up here at the equation that we inputted earlier, there's a mistake because the heat of formation of an ideal gas is on a per mole basis. But if we look at the heat capacity of an ideal gas, it is on a kilomole basis. And so what we have to do to account for that error is to divide the entire heat capacity equation by 1,000, and that will give us actual accurate values. And so now that we have corrected their error, we can move on to calculating the number of moles going in and the number of moles going out. So for moles going in, we have two arrays. We have the arrays for the fuel as well as the uh, the oxygen and the nitrogen. So we're going to combine these two arrays, and so we're going to use np.concatenate, not consecrate, concatenate, and that's going to combine two arrays. And so we want to combine fuel with np.array of the NO2 values and the NN2 values. And then as for the carbon dioxide, there's none going in, and there is no water going in. And then shift enter. So now what we can do is write out arrays for the number of moles going in and the number of moles coming out. So for the number of moles going in, we have this array up here already of the fuel. So we need to combine that array with another array of the number of oxygen, nitrogen, and carbon dioxide and hydrogen moles going in. And so we are going to use numpy.concatenate, and what this will do is it will combine the two arrays. So we want to combine fuel with another array, and this array is going to have the number of moles of the oxygen as well as the number of moles of the nitrogen. And as for the water moles and the carbon dioxide moles, there are none because this is what's going in. And then we also need to have the number of moles coming out. And so that is going to be an array as well. And there are no moles of the fuel going out for all of the fuels because the fuel is being used up. So that's methane, ethane, and propane. And then there is no oxygen being used up, or the oxygen is also being used up. So there's none of that left. As for the nitrogen, remember there is excess air, and so there's going to be the nitrogen moles multiplied by the excess air. And then the number of carbon dioxide and the number of water moles. So that is what is coming out. And so if we were to multiply the enthalpy, let's say 8 at any given temperature, we'll do 1,000. So we have those enthalpies, and then we have the moles going in, if we were to multiply those two values, multiply those two arrays, that would give us the enthalpy per mole. So if we were to do the dot product, which is multiplying these two together, that gives us the temperature. And so if we were to do that, that gives us the enthalpy, excuse me. And so if we were to do that for the moles going in and moles going out, we can see that we get two enthalpies here. And so we want the enthalpies to equal one another because, as we said in here, the enthalpy going in has to equal the enthalpy going out. And so if we were to change the temperature, let's say we change this to 900, we would have to manually, slowly change the temperature until they were equal. But what else we can do rather than just inputting temperatures and hoping that eventually they'll equal the same is create and define a function and use the root function to calculate the root of two equations that are set equal to 0. And so what we can do is define a function, and we are going to define an equation, and since it is calculating the root of simultaneous equations and simultaneous functions, it's going to be in array form, and so what we have to do is we have to unpack this array. So we want the temperature, and that's going to be equal to the first value in the array. And so we want it to return the enthalpy going in minus the enthalpy going out. And again, simultaneous equations, simultaneous variables, so it will be an array, so we have to put brackets. And so now what we can do is we can use the root function, and it needs the function, the equation that we are trying to solve, and then it needs a initial guess. So we can say our initial guess is 2000. Shift enter, we are given all of these values, and so we just want the x value and we want the first index of it, and so that will return us the temperature that is a scalar value. So as we can see, the temperature cannot be negative of a flame, so there's been an error made. So if we scroll up and we look for the error, we can see that the initial temperature going in is at 298 Kelvin, and so we don't want it at the T value, but we want it at 298. Also, it should be the root to shift enter. Another thing is up here, there is the excess nitrogen, but there's also an excess in the oxygen, so it should be NO2 multiplied by the X air. So if we shift enter. So going back, we can see that there's another error that's been made. So if we look at this integral here, we found the integral of the second and third terms, but we did not integrate the first term. So if we were to integrate the A with respect to T, the integral of A with respect to temperature is A multiplied by temperature. So adding that into our equation, and then adding that into our code, That will give us the correct final temperature of the flame.